Hello everyone, I'm Bill Kaiser. I'm going to be telling you today about our new freshman curriculum in electrical and computer engineering. It's been a terrifically exciting, successful new initiative. Right now, we're in the laboratory where our instruction takes place. So in the next few minutes, in the presentation that's about to start now, I'll be telling you about the freshman curriculum. Our new freshman curriculum is focused on the Internet of Things. It's intended to provide a rapid start, inspiration, motivation, and fundamental learning, and career preparation in electrical and computer engineering. It engages all students in personal design challenges, accelerates learning, and we introduce sensing, signal processing, machine learning, and everything else in the Internet of Things. And we prepare students for undergraduate academic success, industry internships, and undergraduate research. And I'll provide some examples of this. First of all, electrical and computer engineering is changing the world with IoT. Healthcare is forever advanced by IoT wearable devices. The self-driving car now does and will always depend upon IoT. IoT is distributed everywhere, along with artificial intelligence. Our electrical and computer engineering field in IoT includes computers that are embedded, distributed, worn by individuals, and part of every life. They integrate sensors, signal processing, computer engineering principles, and wireless communication. In our course, we use the world's best, the most dense IoT platform, the ST Microelectronics sensor tile. And we have a close partnership with ST Microelectronics. This device incorporates a state-of-the-art processor, Bluetooth Low Energy communication, and multiple sensors, a microphone, the world's best MEMS motion sensor. We teach IoT through an accelerated process where all students complete a set of tutorials that we've developed and reference designs. All these are open source and online. All the students join teams and select really compelling missions after having completed their tutorials and reference designs. This is now distributed, and ST Microelectronics made an announcement of this the other day, and their announcement produced a record for them in number of hits to their blog on the UCLA curriculum. It's adopted worldwide now. It's also been adopted by professional engineers and professional engineering organizations. Developed here for freshmen. There have been many exciting IoT project missions. For example, last quarter, here in fall, gesture and motion recognition, motion control of audio systems, platform localization. Students developed resistance training guidance, rehabilitation guidance, detection of gait disorders to reduce athlete injury risk. There are many students I could talk about. We're so proud of our E96 graduates. Many of our E96 students become mentors in following courses. So, for example, these students will be mentors this quarter, here in spring, and next fall. Susie Tam, who's now a junior, developed an IoT mission on sensor tile. She's now a researcher in machine learning and a mentor. Alex Graining developed a sensor tile system for improving basketball free throw. His system is now in use at other institutions. Harvard University's extension program used his design in their course this last fall. Gillian Vaughn, she's now a sophomore, developed sensor tile characterization of swimming motion efficiency. And I'll tell you about Charles the Loon. He was introduced to machine learning and IoT in E96, and then entirely independently invented embedded ML, the first complete self-train and execute neural network system operating on a microcontroller. All of our students learn about neural networks and machine learning, and they learn about this construct that you may have heard of. The neural network accepts a set of input signals with the objective of using these input signal values, interpreting them, to make a prediction about the state of, for example, a patient wearing sensors. The output signal is a classification. The neural network uses computing elements, these neurons, resembling neurons in the human brain, and synapse connections. These neurons, computing elements, each contain a means to compare an input signal with a threshold. If the input signal exceeds a threshold, then the neuron fires a signal to other neighbor neurons, which then sum inputs and compare them against the threshold and propagate information through the network. Well, as you might imagine, these thresholds can be programmed so that a greater signal value or a smaller signal value may lead to the neuron firing at its output. Well, even the weights that connect neurons and lead to an enhancement of the contribution of one neuron to a sum of inputs for many neurons, even this can be adjusted. And all this can be programmed. But what's most important about neural networks is that through a beautiful mathematical process, the neural network can learn. That is, we can present to the neural network output signals that are proven to exist for a given set of input signals, and then train. Given enough input signals and their corresponding outputs, the neural network can be trained so that when a new set of signals arrives, never been seen before, the neural network may accurately classify the output. Well, that means recognition. So Charles developed a new generation of neural network systems here. Previously, a neural network required a large-scale computer for operation. His device operates on a sensor tile microprocessor. Here's a demonstration. So there's the sensor tile device. That square right there that I'm pointing to here is actually the sensor tile. It's connected via a cable to this computer. But this computer here in the background is providing no computing support. Everything is occurring on the sensor tile. And Charles' system can be trained to recognize various events. This one will be trained to recognize orientation by measuring the acceleration due to gravity and how it changes when the sensor tile is moved. For example, right now, the sensor tile is learning. It's telling us to move it to the right, to rotate to the left, to hold it up, and to hold it down. After a series of these, it has enough data to begin learning. And now it's learning. That's what's indicated there. And it has learned. And it's now predicting. It can detect up, right, left, forward, backward. I could talk about this for a long time, but we have to continue on. But you may learn more about Charles here at this link, and certainly contact me or Charles for more information. Embedded ML, independently developed by Charles, is now a corporate focus for ST Microelectronics. Their artificial intelligence group was developing a neural network execution system they had never heard of a system like this that integrated training and testing. So it's a very exciting future. Ahead of us, we have many new platforms, new sensors, new software, new machine learning, new control systems. And in summary, E96 is dedicated to advancing computer engineering, promoting student mentorship, and building careers. So please do contact me with any questions.